More sewing.
But by the way, like that one Mac Mini, the older one, 667 megahertz processor and 512 megs of RAM.
It's not a 67 megahertz processor.
667.
667?
Yeah.
Really?
Yeah.
Solo? Core Solo?
Yeah. I was like,
that should still be able to buy it.
Really? I think.
I think it will.
Graphics card support WoW?
I bet it will.
You're gonna use it to buy.
I bet it will.
That's what I want one for. The other one, I'm having a fun time loading or erasing.
All right. So last time we were talking about home networks versus enterprise networks, and we saw this example here of an enterprise network similar to what we'd have here at Concordia, where you have your what I referred to as the edge router. They called it an institutional router. Then you have a couple of sub networks in here, and these guys are talking to each other through this edge router. So there's a data connection speed between these two subnetworks, and then within each of these subnets, there's a data connection speed governed by each of these switches. All right. We started talking a little bit about wireless networks and some of the cellular equivalents. So 3G, 4G, LTE, kind of how 3G and 4G is a catch-all phrase for the third and fourth generation networks from various providers, but each provider might be using a different technology. So you'd have a very different speed experience.
Also rate.
Yeah, HSPA is it's a GSM-based network prior to AT&T's LTE.
So is it considered 4G or is it better than 4G?
Well, no, it was both 3G and 4G. So that was their technology they used at AT&T. It was a GSM-based technology that bridged from 3G to 4G.
Okay.
Then LTE is the replacement for that.
GSM, UMTS, those cross-sector exit 1921.
All right. So in any case, all of these guys here kind of are examples of wireless networks. Okay, so we're using airwaves to send data somehow. All right, so this kind of goes with what I was saying at the beginning of class last time. I still want us to try to think about these things as communication networks rather than the internet. Okay, because in today's world, we want to think of everything as internet connectivity. You know, how can I check my email? How can I do these other things as opposed to computers talking to each other? Okay, so we want to start thinking about how information is sent over these communication channels. So we have this idea of a packet. So think of like sending a letter in the mail. So certain things are required in order for it to arrive at its destination. So you have to put return address. You have to put the destination address. You usually got to throw a stamp on it. Then you, of course, have to put your data inside the envelope, that kind of stuff. You put it in the mail and you expect it to arrive at the end point, right? Now, a lot of stuff has to happen in the middle. So when you drop an envelope in the mail, where does that go?
Santa.
Okay, it goes to Santa. Where does it really go?
To Grandma.
It magically pops up at Grandma's?
No.
Okay, what happens in the middle?
Goes to a post office.
Okay, just one post office?
I go through the truck first, then the sorting facility.
Okay, so let's start this way. I walk to the end of my driveway, and I put an envelope in the mailbox, and I put the little flag up. Who's going to grab that mail? The person comes by in the mail truck. Okay, what are they going to do with it? Bring it to the local post office for the place they work, right? And what's going to happen to it in the local post office?
Sorted for general area.
So it's going to they're going to throw it through a sorting program to determine, is this local mail or is this mail that goes outside of this town, right? If it's mail that goes outside of this town, where does it go? Onto an outbound truck. And where does that truck go? Probably a less local but still relatively local sorting facility, right? Because what if you're sending the mail to Wauwatosa from Grafton, as an example? Well, it's certainly not going to get flagged as Grafton mail, but you don't want it to go all the way to California before it comes back to Wauwatosa. So it's going to go through several sorting facilities until it gets to a local destination, correct? And go more and more, well, larger regional things until it finally gets there. Finally, it's going to get out on a truck for delivery. We experience this when we're tracking our UPS packages, right? We see our UPS packages or our FedEx package, we see it, being picked up, arrived at international office here, on airplane, blah, 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 on truck for delivery. So we see all those individual steps, or at least the ones that they decide to display to us, okay? Well, does the envelope always arrive? I mean, it should. Most of the time it arrives, correct? But has the post office never lost a letter? How many of you have ever received somebody else's mail? Most of us, right? Okay. They're human. They make mistakes. Okay. I always find it's funny when they're not even anywhere close to the same street.
Or the same city.
Yeah, same city would be a bigger issue.
I got one of those once.
In any case, let's say that a letter doesn't arrive. So you're sending a letter to grandma and it didn't arrive. Does anybody notify you it didn't get there? No. Eventually you have a conversation and grandma says, I never got the letter. Right? Okay, so nobody's notified that the delivery didn't happen. Post office lost it somewhere in the middle, so they aren't going to notify you that something bad happened. They can do some investigative stuff to try to figure out who dropped the ball and where. But bottom line is nobody's actually notified. So what's your solution? Grandma didn't get the letter, what do? Send it again. Put a new letter out in the mail. Right? Okay, but somebody had to notify you. So sending a letter, something we think is being very simple, has to go through a lot of complexities before it actually ends up getting there. Okay? So when we think about the mail network, that is our entry point locally would be at the mailbox at your house, which then jumps on the connection that is the mail truck, which goes to a router, which is the post office. The post office determines, do I reroute this internally on my local network, or do I send it externally to some other network? Okay, so it gets on a truck going someplace else. Sometimes there's going to be airplanes involved, whatever. All of those are communication links. Make sense? Okay, that's exactly how a computer network works. All right, so we have our highways, our Ethernet cables, copper, Wi-Fi, whatever. The way we are talking, communication channels, those are just like our roads that the mail trucks are driving on. And we need to package our data up in some sort of interesting way so that it can arrive at its destination. Now, let's say that we are sending a relatively large file. So by today's standards, let's just say it's a 1 gigabyte file. Okay? So by today's standards, a 1 gigabyte file is probably something along the lines of shipping a dishwasher. I think a dishwasher weighs about 1 gigabyte. Make sense? Okay, well, it is in this example. Okay, so dishwasher weighs 1 gigabyte. Okay, if you're going to ship a dishwasher, what do? Find a big box, put dishwasher in box, take it to probably UPS store.
Called UPS.
Try not to cry while they're weighing it and telling you how much it's going to cost. Tell them you don't even want to know what the overnight charge would be. I want this ground or slower. Okay.
Put it on a cable.
Okay. So your options are very limited. Why? We can't chop up a dishwasher and send it there in little pieces and hope that they put it back together on the other end. Now, when the store first got the dishwasher, the assembly place, the dishwasher is just a combination of a whole bunch of parts, right? And those parts may have come from different vendors. So at some point in time, what ended up being that dishwasher object was a whole bunch of little pieces that were shipped to one place who then assembled them. Well, if you're shipping somebody a dishwasher, if you go and buy a dishwasher at Best Buy or an appliance store or something like that, they're not going to disassemble it to you and send it to you with the 650-page instruction manual on how to put this thing together. You're expecting a full dishwasher. right? Okay. Now, at the same time, they're not going to ship you 50 packages with that 650-page instruction manual and then have a guy show up to your house and put it together either. It doesn't make sense for a dishwasher. Dishwashers show up already in one piece. If you have a guy, all he's going to do is he's going to install it. Probably take out the old one, put in the new one, make sure the water lines aren't leaking. That kind of stuff, right? Okay, so we have a means by which certain things, certain specialty things, arrive at their destination. Okay, but heavy objects are more difficult to deliver than light objects, but we go through the exact same process. Now, let's say you've shipped this dishwasher, and I know UPS always is very, very careful with the packages. Okay, and it arrives, and there's a gigantic dent in it. What do? Well, you might try the dishwasher first. Maybe there's a giant dent in the box. So then you open the box very carefully, and you're hoping that the dent did not get through the packing material, right? Okay, so let's say it didn't. The item doesn't appear to be damaged. Well, now you got to plug it in and find out if the jarring that had occurred maybe did some more damage than might otherwise be evident. Okay, so you plug it in. Maybe everything's working, maybe it's not. Let's say it's broken. What are the options?
Call UPS.
Okay, well, you're probably going to call the place you bought it from first and say, something bad happened. The box was all damaged, here's some pictures, blah, blah, blah. They're going to file a claim with UPS because they probably shipped it with insurance, whatever. But at the end of the day, you don't care about that. You paid for shipping. You paid for a dishwasher. You want it to work. So what can they do? They can either send you a new one, so resend the dishwasher, or they can send somebody out to fix the dishwasher. See what's wrong with it, right? Okay. From your perspective, you may not care as long as in the end you have a reliable working dishwasher. But in principle, most people are like, look, I've never used this dishwasher once. I want a new dishwasher. Right? You know, who knows what they're going to find when they come out and what, well, maybe the bigger thing is what they're not going to find wrong with it that actually is wrong with it. All right, so we have some limitations when we're dealing with physical items. So we have an advantage when it comes to sending data over a network. That is, data is a stream of zeros and ones. Just a whole bunch of single digits. Zeros and ones, zeros and ones, zeros and ones. And can we send those individually? If we are sending the digital version of a dishwasher, a 1 gigabyte file, let's say, do we send that in one big fell swoop? Or can we stream it to somebody one bit at a time? Modern technology, things like Netflix, we wouldn't even be able to enjoy if they hadn't come up with tools for streaming data. You know, historically, if you wanted to watch a movie, you had to download the entire movie. And then once it was completely downloaded, then you could watch it, because you used a local tool to decode it. Well, now you can start watching any of the thousands of movies that are on Netflix in seconds. Cool enough. Now, we all know that not all of the movie is local on our machine when it first starts. But as long as it keeps up, as long as it's at least, well, I guess as long as it's at least 1 second ahead of us, we'll be okay. But we probably want it to be about 30 seconds at least ahead of us so we get a little bit of wiggle room if there's a hiccup in our internet. Okay, so we have to talk about what are different ways we can send data across a network. And part of this deals with the evolution of these networks. So when a host sends something, so we're going to take an application, break it into smaller chunks. In modern day networks, our modern day networks are called packet switched networks. Okay, so we break our dishwasher up into a whole bunch of little envelopes, a whole bunch of little packets, and we send them one packet at a time through the mail. Okay, one right after another one. So each packet has a length associated with it, and we'll come back to that here in a second. We're going to transmit the packets onto the network, put it onto the mail network, whatever, at a certain speed, however fast the mail truck goes. This part's not really important for this. Okay, and ultimately, some or all of those letters are going to arrive. All right, so let's think about this in terms of a book. So instead of mailing a single book, let's say you're an author and you wrote a book and you're real paranoid about somebody getting their hands on your book, you're going to break your book down. So we're going to say it's a 500-page book. You're going to mail the book to the publisher one page at a time. So you're going to create 500 envelopes. Well, you'll buy 500 envelopes. Put one page at a time into the envelopes, put stamps on all of them, and mail them to the author, or to the publisher, rather. So they're going to hopefully receive 500 envelopes that they then need to reassemble into a book, right? Okay, are they going to be able to do that? First of all, if you sent 500 different envelopes at the same time to one recipient, how confident are you that all 500 of them would arrive? By today's standards, we might even feel pretty confident. But would we be surprised if one of them did not? That probably would not shock us, right? One envelope slips through the cracks or something like that. Okay, so let's assume in our first example here that all 500 did arrive. All right, now, can they reassemble that book? Only if we numbered the pages. What if we didn't?
They know the book really.
Huh?
Be one weird book.
Well, one weird book when reading it in certain orders, right?
Choose your own adventure.
Yes, choose your own adventure. So, bottom line is, there's no guarantee that those envelopes will arrive in any sort of specific order, right? Okay? I mean, there isn't a guarantee. They will likely, by the way our mail system works, probably all arrive on the same day, but they might not, for whatever reason. You know, there might be some situations in the middle there where mail is split between two sorting facilities, and some of your envelopes go to one, some of them go to the other, and it might take an extra day for some of them to arrive at their destination. So, first of all, there's no guarantee the order you're going to actually receive the letters. So the publisher. There's no guarantee what the order they'll receive the letters. So they can't reassemble them that way. If we gave them page numbers, they could reassemble them that way. Okay? So we're going to add page numbers now. So we feel okay they're going to be able to reassemble them. All of a sudden, they're probably pretty pissed at the author at this time. They're reassembling 500 pages, and they find out they're missing page 403. So now the question is did the author forget to send page 403, or was 403 lost in the mail? So what are they going to do? They're going to contact the author, make him aware that page 403 is missing and needs to be resent. Author's going to turn around, resend page 403. It's eventually, hopefully, going to arrive at the destination, and they'll finish assembling the book. Make sense? The high level, we just described TCPIP. That's how our modern packet-switched networks work. All right? They break data up into small pieces. They send the data to the destination with no guarantee in which order that data will arrive. The data is, though, organized in such a way that it can be reassembled on the end. And if pieces of the data are missing, the sender is sent a request to resend only the pieces that are missing. That make sense? Okay. That's our TCP/IP networks today. Now, if we're kind of brainstorming this, what are the size of the packets we should send? For our author, we use the example of one page. Why did he pick one page instead of sending it in 10-page chunks?
Smaller bunch means less data loss.
Okay.
Losing one page rather than 5 pages.
Okay. So keeping with our U.S. mail, U.S. Post Office example, if instead of sending 500 one-page things, we can send 10-page bundles, Okay, so we'll send 10-page bundles. So we're going to have less envelopes that we're going to ship out. Now, if one envelope doesn't arrive, then what?
Big chunk.
Well, now they got to request somebody to send 10 missing pages instead of 1 missing page. Now, if you're sending pages one at a time, how do you think it's likely that you would miss 10 pages? Or at most, would you lose 1 or 2? Probably at most you'd lose 1 or 2 pages, right? So isn't sending in 10-page chunks actually problematic?
Mhm.
Now you lose either 10 or 20 pages, depending on which things didn't arrive. Well, so does that mean that sending 10 pages at once is worse than sending 1 page at once?
No, but sending 10 pages, we probably won't lose anything.
Probably wouldn't lose anything.
Yeah.
Probably wouldn't lose anything sending 1 page at once. But we're already acting a little crazy. They wouldn't just send the book. Right? All right, so what's the advantage of sending 10 pages instead of 1 page? Go ahead.
You don't have to send as many things.
You're going to send less crap.
The assembly is faster.
The assembly took less time. If I'm going to put together 500 envelopes and put a page in each one, that takes time. Okay? And plus, you got to think about the efficiency of it from the perspective of the amount of stuff I'm sending. If I'm using 1 envelope to send 1 page, I'm essentially using just as much packing material as I have data that I'm sending, right? The envelope plus the stamp plus the ink, let's call that equal to the 1 page of your book. That doesn't seem very efficient. Okay? Well, just because it's not efficient doesn't mean it won't work, but people are going to look at you a little crazy, and that publisher probably isn't going to work with you again. Okay, so we'd rather send in 10-page chunks. What about 50-page chunks? Send 10, 50-page. We're getting more reasonable, right? Go ahead.
If you get too big, you have to take up a lot of space on the highway where you might hit somebody.
I think taking that back to our data network example, at a certain size, you're right. I don't know that in this case the 50-page example quite hits that, but certainly the larger the vehicle, the larger the packet, the better chance of a collision, that there will be some damage. Right? So if you're driving a school bus blindfolded on the interstate,
How we play.
there's a better chance that you're probably going to ding into something than if you're driving a motorcycle blindfolded on the interstate. And they both have high likelihoods that you're going to hit something.
It's gonna be
Okay?
a
We're just
bad
saying
day.
comparatively, comparatively, your chance of randomly missing stuff is better on a tiny motorcycle. I mean, we're talking like a Vespa, okay, something like that, than in a school bus. So I guess it's just the thing. So now, in real life, wouldn't we just send the book? Most of us? Send the whole book.
If you want to be a dick,
What's the danger of that?
they lose the whole book.
They lose the whole book, and then what do we need to do?
Buy another one.
Well, we wrote it. We got to print the whole book out again, right? Is printing a 500-page book somewhat cost prohibitive? We start seeing where this is going, right? You know, you're going to print 500 pages. You know, it's the cost of ink and all this stuff. So, you know, maybe that's not a reasonable risk. At this point, when we're sending it using the post office, we better trust them. If we think there's a 50-50 shot that the post office is going to lose the book, we might be less likely to send the whole book at once. We might want to send it in smaller pieces, right? Kind of see where this is going? All right, so it's a matter of early on these different networking protocols, the languages that we were using to send things from one point to another point over a network, they had to figure out kind of what's that sweet spot. What is efficient enough that you're not spending all your time packing, and what's not so inefficient that a data error is going to require you to resend everything. So we got to find that place in the middle. Okay, and that gets into our packets of length L, however many bits they are. Okay, so physical media. A bit propagates between transmitters, receivers, pairs. So a bit is running down your copper wire or something like that between two pieces of equipment, whatever. The physical link is what lies between. That's your copper. Guided media. This is along hard things like copper, fiber, coaxial cable. So your cable network, telephone network. Fiber is still guided because it's light bouncing off the walls of the thing. Doesn't matter. Unguided would be things like radio, where it just propagates freely, and we have tools that just sample the air and try to pick up what it can pick up. That's why we run into some problems sometimes, like on campus. You might find a place that has very good Wi-Fi reception, and then 3 feet from there, you have no Wi-Fi reception, because there might be something with the power lines going through the wall or something like that that's creating enough interference that your wireless radio inside of your laptop or your phone or whatever isn't able to sample clear signals from the air, just because of where you're standing at that moment. Okay, as opposed to guided media where we know where the pitch is coming. Right? Like if you're standing there with the hose pointing to your face, you know that when somebody turns the water on, it's going to be bad. Okay, so guided media versus unguided media, not really important, but they both exist. This idea of twisted pair deals with copper wires. So you'd have insulated copper wires. Have you ever opened up a Cat5 cable? There are 8 total cables, but 4 twisted pairs. So you'd have these little copper cables wrapped along each other, but each of them is insulated among themselves. Part of this is to keep there from being too much interference, and it comes down to collisions and this kind of stuff. So you do have this idea of a twisted pair. Twisted pair would only exist in guided media. Really, it only exists in copper guided media. Okay, if anybody ever starts talking about twisted pair as it relates to Wi-Fi, punch him in the face and run. You don't want to be talking to him. Probably a Best Buy employee would be my guess. Could be. Okay, so let's talk a little bit about some of the physical media. So coaxial cable, 2 concentric copper conductors. If you've ever looked at the end of a coaxial cable that didn't have the point on it, you would see there's a kind of a solid core and then another piece around it. The interesting thing here, and this kind of goes back to our discussion before about cable modems, the early cable modems needed a dial-up connection. Well, right here it says that a coaxial cable is bidirectional. Does that jive with our does that jive with our concept of the early cable modems needed a dial-up modem because they couldn't send requests?
Did they just not know how to do that?
Who?
Did they just not know how to do bidirectional on a coaxial cable?
They didn't. Why? What were we using coaxial networks for?
Sending things one way.
Why?
Broadcasting.
Yeah, it was for TV, right? Coaxial networks were used for TV. And TV is a broadcast type technology. We send the channels out, and everybody else is just receiving them. So those boxes that are sitting in your house for your cable company, the early days of those were only receivers. They sampled the line, and they couldn't send anything out. They weren't designed for that. So that's why you had all of these pieces of equipment in these people's homes that couldn't send. You also had all these really, really, really expensive pieces of equipment in the cable company's home office that couldn't receive. That make sense? So, kind of makes you hate cable companies that much worse, because the biggest issue early on was probably they didn't want to replace their equipment. Because what's in between is just coaxial cable. It's wire made out of copper in a certain way. How they're using that cable is what was the limitation on the technology. All right, so coaxial cable is bidirectional. There's multiple channels. You see there's a twisted pair in there, as well as a external core. Fiber optic, is that actually an example of fiber optic, or is that like a dying snail?
It's a hand holding fiber optics.
Oh, I see it now.
Oh, I do see it now.
I didn't see that originally.
What's on your mind?
I'm thinking dead snail. Well, maybe not dead. He still has a little glimmer in his eye here. See, you guys are seeing what I'm talking about now, right?
Oh, I saw it.
That's not.
Yeah. So all of these are little endpoints of the fiber optic cable. Okay, that's that.
I was really confused when I first looked at it. Like the one that's in the pinched in the fingers looks like a
I
little
thought these
eye or
were his
something.
little legs.
Yeah.
His little snail, dying snail legs. Well, not legs. I mean, snails are kind of like really, really, really slow, like hovercrafts. They're sticky.
Biology was never your strong suit.
You know, I haven't seen in years. I haven't seen a slug. I haven't seen a slug in years. I haven't seen one of those. What are they roly polies?
Oh, yeah.
I haven't seen one of those in years. Are they extinct?
No. Want me to bring some?
Go outside.
With a pickaxe right now.
Same thing when I was a kid. It seemed like there was lightning bugs out all the time. I don't see lightning bugs as much either.
Well, it depends on where you live.
Yeah, I mean, I grew up in not the sticks, but significantly closer to the sticks than this. You know, little rural Illinois town. So, Rantoul, Illinois, near Champaign.
Oh, I know that.
Yeah. So, anyways, we got the dying snail and his little dying legs, and the last glimmer in his eye. So fiber optic cable is a glass fiber carrying light pulses, each pulse being a single bit, and it's kind of bouncing off the walls of this, so that's how it propagates. High speed, point to point, whatever. Low error rate repeaters, spaced far apart, immune to electromagnetic noise. So the idea with that is if you lay a magnet on top of a fiber optic cable, that's not going to affect light. You lay a magnet on top of coaxial cable or with the POTS network, it's bad. Because the bits are literally traveling over the copper and it's an electrical signal and it will be redirected by the magnetism. It's bad.
Do snails have an adverse effect on any of these?
Yes.
Dying snails.
Dying snails. Glimmer of hope. Glimmer of hope. All right. Radio. It's funny how they call it physical media. Radio. So signal is carried in electromagnetic spectrum. Okay, so it's a broadcast type thing. It's just out there. There isn't a physical wire. It is it's biodirectional, as the dying snail indicates. That's the bio part of it. So it's bidirectional. Propagation, environment effects. We have reflection, obstruction by objects, and interference. Reflection is actually a big deal. Have you ever been in a building that's made of metal? You get a lot of signals bouncing off the metal walls, and therefore the data actually doesn't get to you. So you might be in a house that doesn't seem that big, and you have a Wi-Fi router, let's say, in the house, and you're standing in the garage, and all of a sudden it's like it just doesn't work, and you don't understand why. You're 10 feet from this thing. Same thing, obstruction by objects. Usually it's going to be something metallic. And then you just have interference. That's other radio signals, other things that are flying around. There's an interesting graphic out there. I'm sure there's several like this, but that kind of shows our world today in terms of radio signals versus the way the world was like in 1900. It's like shocking. So it's kind of like we're constantly submerged in the ocean right now. There's so many radio waves and stuff flying through our bodies at all time. It's kind of awesome, actually. So, like the people who complain that you hold a cell phone up to your ear too much, bad things will happen. If that was the only radio signal that was hitting your brain, we wouldn't have that much to worry about. But So if that ends up being a problem, we're all kind of screwed. So just prepare yourself. Radio link types, terrestrial versus microwave. So microwave is going to have a much higher, terrestrial microwave, which is going to be microwave, kind of probably similar to what you have. This is all on Earth. So from place to place, a high-powered signal. We have a local area network like these boxes right here. That's going to, that's not going to use microwaves. Like you probably would not want to go and lay on top of a microwave transmitter that's keeping the internet going. Things could start bubbling. That's a lot of power it's putting out. Then you have your wide area type stuff, your cellular type things, which aren't going to be as directed as microwave. These things are much more wider spectrums, where microwave is kind of a single beam of destruction. And then you have satellite type stuff, which is going to start bouncing stuff up into space. That way we can, get from here over to the other side of the world without boring through the center of the Earth, which would be a obstruction by object example when the Earth gets in the way. Go ahead.
With CDMA and GSM, isn't CDMA networks a tighter band, closer to a radio band than GSM? Because I know
They're both radio bands.
Yeah, well, I know CDMA technology. You can have fewer towers because the band or the signal can actually
Goes farther
because it's a tighter band. And GSM, you have to have more towers closer together.
Yeah, but I don't think it's because of the size of the band. The nature of CDMA, it's a cell division multiplexing. It's the way the packets are organized, is less.
You get less data loss over distance.
That's it. That's it. You get less data loss over distance. And so you've probably noticed this if you've ever tried to play a game over a CDMA technology versus a GSM technology. CDMA typically has substantially longer or substantially worse latency because they're having to travel farther to get to the tower. Where that's always the history of this is, how Verizon typically has less dropped calls than AT&T. Well, it's because AT&T is switching towers every 5 seconds because they're GSM and you're constantly handing off to the next tower. So the very thing that makes their network fairly fast with low latency is the same reason why they're dropping calls. Because that handoff between two towers while you're still talking is, yeah, I mean, it's not an easy problem to solve, and they've solved it well, but when you're switching towers, let's say 100 times between here and Chicago,
At least.
There's lots of opportunity for things to mess up. All right. So, yeah, I don't know that it's fair to say it has anything to do with the band itself. I think it's more the technology that they're using.
That's one thing I've been wondering for a while since I built AT&T's towers.
Okay, so we looked at the. So we just looked at network core, so let's look at data loss and stuff. We're on network core now. Oh, this is the details of what we just introduced. Okay. So network core, this is the mesh around the interconnected routers. Fine, whatever. Packet switching, hosts, break application layer, messages into packets. So we're going to be talking about our network as several layers all connected together. We'll see what this book introduces, but typically you have either 5 or 7 layers. They're all the same layers, just the 7-layer model splits apart a couple of the layers into individual layers. Okay, so we'll be talking about those layers that this book happens to decide are important. So forward packets from one router to the next across links on path from source to destination. That's our post office. That's the post office model we looked at, where our letters get on a truck and go from one sorting place to another sorting place, and it gets routed ultimately to its destination. Okay? You can also think about this like in terms of airlines. If you're flying to Los Angeles from Milwaukee, it's entirely possible you might first fly to Georgia, Atlanta. That doesn't seem to make any sense. You would never drive to Atlanta to get to Los Angeles, right? Well, Some people might, I
know
suppose.
those flights.
Okay. Okay. I suppose with some of the new laws in Colorado, you might drive to New York by way of Boulder or something. If you didn't get that, I'm sorry.
Let's go to Seattle before we go to Florida.
Well, Seattle doesn't have any laws yet, so stock up on baked goods.
Gotta go to the herb store.
Yeah.
It's legalized in Washington?
Yeah, it is.
They made a joke about it when the Seahawks and the Broncos were in the Super Bowl because
Yeah.
the two teams that just legalized.
Oh,
The
I didn't
two
know. I
teams
didn't
are-
know Seattle was.
Two teams that legalize marijuana are going to a Super Bowl. I bet there was some deflated.
There was a. I think it's fairly recent. There's a comedian. His name's Ralphie May. I think he recently did a show, or maybe not super recently, but very shortly after they made marijuana legal in Colorado. He was giving doing a show. Apparently, he hit the snack food pretty hard. They had to cancel the show like mid-show. This guy was high as a kite. He couldn't even function. There's a YouTube video out there. You can't show it in class, but it's.
What's his name?
Ralphie. You never heard of Ralphie May?
No.
Oh, I love Ralphie May.
Got it. Okay, it's in my notes.
All right. Let's see. So this is our post office. Each packet transmitted at full link capacity. That means you're going to use the full capacity of the highway.
Why wouldn't you?
Exactly. All right. Packet switching, store and forward. This is actually an important evolution of the idea of resending data. So to kind of explain this at the high level before we look at the details of this, let's go back to our example of the post office, where we're sending data we're sending a letter from here to California, let's say, and there's a chance that one letter gets lost in the mail, correct? Well, by our original example, by our real life example, if the letter gets lost and it doesn't get there, we have to get notified all the way back at the beginning that we have to resend the letter. But what if at every single router, every single post office, or at some strategic post offices, the letter was duplicated? Okay, so they made a copy of the letter and then sent it on. So that, worst case, the letter at least made progress towards its destination. Does that make sense? Let's say it ended up getting lost at the local post office in Los Angeles. So got lost in the truck, something like that. So that's where it went. That's where it went south. Well, then they could just go back to the local post office and get a copy and go and redeliver it. They didn't have to go through the whole process of having you send it again. Seems like an efficiency, right? Well, that works great when we're dealing with digital data. Doesn't work as well when we're talking about them making copies of our personal mail. So we can start seeing some advantages with computer stuff, and we can kind of leverage that. So that's the idea of store and forward. Understand, though, that the time it takes to store something will reduce transmission speed. Does that make sense? If you're, I guess think about it from like sending an email perspective. When you send an email, it doesn't just instantly arrive. It does. I mean, even the fastest email is going to take a couple of seconds before it'll arrive there, right? Very likely that email is being copied onto various servers, temporary storage, just in case it needs to be retransmitted. That's only part of the delay, but the idea is the more times you're going to copy it, the more time it's going to take to send. So again, there's this balancing act between performance and accuracy. How many times do I duplicate the data so I don't lose it, or it takes less time to retransmit it, as opposed to just getting it there as fast as humanly possible? All right. I guess it's kind of like the same reason as like with these bullet trains you're starting to see around the world. that they don't just strap a person onto the tracks and say go. They kind of surround you with walls and stuff, and they give you seatbelts. Man, wouldn't that be scary? They just put you in this. You just like face first, 400 miles an hour. Just you're just seeing these things fly.
I want to try this. I ain't puked in a while.
One of the bullet trains.
Yeah,
Feel
duct tape you to the
Duct
front.
tape.
Duct tape you to the front of this.
Duct tape.
See how much.
Dies.
Let's see how much you trust duct tape now. 400 miles an hour in random weather conditions.
Hell,
a lot of duct tape or
We gotta have enough to go around the whole train. I'm not just want it to lock.
Never seen a man start on fire that fast.
What's this?
Never seen a man start on fire that fast.
Fast.
The bird actually went through him.
Else have you seen a man start on fire?
Well, you
there's
can see it on
one
TV.
time- No.
Yeah,
A man starting on fire?
yeah. There's all sorts of stuff like about like some of those like
That's serious.
unsolved. Earlier today in my office. I was watching Bones, and this dude was lit on fire in a church. Guy had horns too. It was like he was supposed to be like a demon. They were real horns. And that's, yeah, the guy had horns, and he had a
Was he like
vestigial.
crossed?
What?
Was he like crossed with a demon?
And it was in a church.
No, like
No, there was.
he,
It was just.
like,
It was.
crossed with
It was a
deer?
guy who was born with like a tail and stuff like that, and decided to take it to the next level and
Oh, I was.
had real horns put on. It didn't have the other stuff taken off, and just.
He was ready for Halloween.
But we were meant to think it might be a real demon because it was in a church. So that was the whole punchline. Okay, so let's just kind of finish this slide real quick. So this idea of store and forward is good from a redundancy perspective, protects our data, and hopefully if we have to retransmit, we're only retransmitting at a minimal amount. When we're talking about networks, something we talk about is the number of hops it takes to do something. For next time, I'm going to give you a quiz. Somebody has to remind me about this. Okay, I'm going to ask you, what is trace route? What is trace route? Traceroute. What is trace route? And it relates to this hop thing. All right? So somebody has to remind me that's what the quiz is at the beginning of class, otherwise you all get zeros. All right, I'll see everybody on Monday.